Okay, we'll continue on for the Exam 1 review, and we will move on to scales and measurement. There's several questions about this. So as you remember, there are four types of measurement: nominal, ordinal, interval, and ratio. And just in general, we'll say that nominal is probably the most unique. We're going to discuss all of them and provide some examples as well. Hopefully a few tips to help you distinguish one from among the others. So nominal data, as the name itself implies, just refers to names or categories. In fact, we use nominal and categorical pretty interchangeably. But the main thing to keep in mind is that the label, the values, whatever is associated with the data, they have no actual meaning other than just being a representation of something. So one of the most common examples you'll see is with gender. Most data sets are going to have one or two or three choices for that value. So it might be male, female, other, or male, female, unknown. Not every data set is going to be the same, but let's just say you ran into a data set that just had male or female. In SPSS, you've come across this where you've noticed that SPSS just loves numbers. It's got to have a number to go with some sort of value. And even if that is nominal or categorical data, it wants a value just because that's how that system works. Now, even though it has a number, that number does not mean anything of mathematical value. It just is essentially a symbol for whatever that data represents. So one of the most conventional ways of handling something like gender, and the numbers don't matter, but it'll give one value to female and one value to male. Now, the best way to help you understand and help you think through this and understand that just because there's a number there doesn't mean this is ordinal, interval, or ratio data. That's one of the things you want to make sure you're careful about, is that just because there's a number there does not mean it's not nominal. And we'll get into a few cases afterwards. But here, one of the things is, let's look at these values. We see 0 and 1 and think, well, those are numbers. Yes, those are numbers, but they represent, or they are just essentially labels for categories. Now, one way to think about this is, look at the values, 0 and 1. They represent female and male in this example. Now, if we say gender is 1, does that mean that male is one more gender than female? Well, no, that doesn't make sense. We could do the same thing with location. Let's say 1 equals Alabama, 2 equals Georgia, and 3 equals Mississippi. Can we say that, Georgia has a value of 2 and Alabama has a value of 1, so Georgia is one more state than Alabama? Again, that does not make sense. So even though there's a number that is associated here, they have no meaning in relation to one another. They could just as easily be some sort of almost nonsensical symbol. Well, for Mississippi, why don't we make that a frowny face? There we go. So they could just as easily be this. So whether it's a number or a symbol, they don't mean anything other than they represent that data. They represent a category. They represent a name. So try to keep that in mind. You may see values. That's what you've seen in SPSS, and that might be causing you a little bit of confusion, is the fact that SPSS, it really wants to see a number, but that number doesn't mean it has mathematical value. It just wants that as a symbol for representing some category. Alright, so moving on, let's talk about ordinal data, which is unique in itself. So the key word with ordinal data, I can't even spell. Okay, the key word with ordinal data is you hear order within that, and that is the key defining aspect of ordinal data. So it has values most of the time, and those values do mean something. So this is the first time where we see values have meaning. So the best example of ordinal data is finishing place in a race. So let's say that this line represents race time finishes. So we have somebody who finishes first, and then someone finishes second, someone finishes third, and someone finishes fourth. Now, the order means something. This person came first, and 2 came second, 3 came third, so the order matters. If you want to say, hey, what place did they come in, you're giving someone ordinal data. Now, even though that order has meaning and it matters, you'll notice that the difference between one number and the next does not stay consistent. So in this example of a race, 1 here may be finished way ahead of 2, and 2 barely finished ahead of 3, and then 3 finished fairly far ahead of 4. So these values, these intervals between values, are not equal. So this is where you start to distinguish ordinal data from the following two, ratio and interval. So order is the key component of ordinal data. The numbers mean something. They stand for a place, a ranking, a placement or a ranking, some sort of order, but the difference between those do not stay consistent. Does this mean that they always have to be a number? Not necessarily. Sticking with this race theme, think about the Olympics. What if I said someone finished with the gold medal, someone finished with the silver medal, and somebody finished with the bronze medal? These are also technically ordinal data, because gold finished first, silver second, and bronze third. Again, how far ahead gold finished ahead of silver is not going to be the same as how far ahead silver finished ahead of bronze, pretty much in any competition we're talking about with the Olympics. So even though you're typically going to see numbers, you could also see something else like a letter grade or words here that would represent an order. The order matters, but the difference between the orders does not stay consistent. And that leads us into interval data. So each one starts to build upon the one preceding it. So interval data has all those same qualities of ordinal data, in that there's typically values. Those values have a meaning. But here's where interval data distinguishes itself. It's going to have numbers, values that have meaning, and each number has an equally spaced interval. It's not a frowny face, it just means those two are equal. Equally spaced intervals. So the difference between 1 and 2 is the same as the difference between 3 and 4, and it's the same as the difference between 5 and 6, and 6 and 7. All these intervals are going to be equal, so it's evenly spaced data. And again, there is a, it matters. 6 is more than 5. 5 is more than 4. However, if we were to continue to extend this line, you see that this is where we distinguish interval from ratio data. So interval data has a 0, but this 0 is just another point on some scale. The best example here is going to be Fahrenheit, temperature measured in Fahrenheit. This is probably the example you also remember from the lecture. So we don't get down to 0 very often in the South, but it is possible to get to 0 degrees Fahrenheit. Does 0 mean the absence, the absolute absence of temperature? No. 0 just means, hey, it's 0 degrees Fahrenheit, and it can go even lower. So 0 does not represent an absence of that data, or an absence of whatever it is you're measuring. It's there. 0 is just a point on the scale. You can then get into the negatives, and that still has a meaningful value towards what you're measuring. Now, ratio, the key distinguishing characteristic between interval and ratio is all about that 0. In ratio data, 0 means there is absolutely nothing there. It means a true absence of whatever it is you're measuring. Now you won't see anyone with an IQ of 0, but if you did, it would mean there is no intelligent quotients there. There is none of that there. If you saw somebody with a weight of 0, it means there is no gravitational pull upon that mass. It is completely absent. You can't go any less than that. There is no negative weight. There is no negative IQ. 0 is the end. 0 means nothing. It's done. Complete absence. So hopefully that helps clear up. A lot of this is just, I'm sure, reiteration of what you have in the lecture, but hopefully there's something here in the example that has cleared up a little bit of this. There was in the discussion asked specifically about ethnicity. Really any kind of variable that you'll get, whether you're talking about the lecture or the lab, if you get a data set and there's a variable for ethnicity, gender, race, location, or something like status, then that is almost always going to be nominal data, categorical data, in that those labels just stand for a category, a status, or something. They don't stand for a value that actually has meaning. So if you did get a data set that had a variable for ethnicity, technically the way the IRB here works, you guys don't have to worry about that, but there are just 3 categories that we have in the research that we do here in our laboratory. We have a separate variable for race and then a separate variable for ethnicity because those are actually 2 different things. And in ethnicity, we have 3 values. It's Hispanic or Latino, not Hispanic or Latino, or you prefer not to answer. The same could be true for race. There are many races. Just to list a few, you could say Caucasian, African American, Asian American, Native Hawaiian or Pacific Islander, and many more. And all of those are categories. Now, if you were to choose one or the other, just like we did with the states here, you wouldn't say that, oh, Asian is one more race than African American. You wouldn't say for ethnicity that prefer not to answer is one less ethnicity than not Hispanic or Latino. So those, even if there were values associated with those values have no meaning in relation to each other. They just stand for a different thing. So if you were to get a data set with ethnicity, you would see a whole bunch of labels, probably like, a race or ethnicity, or oftentimes group status, control group versus placebo group. You can't say that the experimental group is one more group than the control group. They're a different group. So they just represent 2 different things. So hopefully that clears some of that up. Okay, so cover one more thing here and then stop this video and do another one. So there was a question on summation. So this is just in reference to the notation that is used. You won't have to really dissect the notation used or generate a specific formula. Again, the test is open book, open note. It is not open friend, open spouse, open tutor, or anything like that. So you will have all your formulas that you may need there with you, easily accessible. So the emphasis that is going to be placed on summation is just, are you able to work with these formulas? Let me give you an example real quick. So you're probably familiar with the formula for average or mean, which is you take the sum of your data, represented by X here, and you divide by how many you have. And that gives you your mean, or oftentimes we also note that as X bar. I'm more familiar with using X bar. When you create a PowerPoint, it's hard to put X bar in there. So you're used to probably seeing M throughout PowerPoints and presentations. Either way, we're talking about the mean. So what you'll need to do with summation and understanding your formulas is, can you work with it? If you were given 2 of these, you can calculate the third. If you were given all of your x's, you can get the sum of x. and then you can tell how many you have, and then you can calculate your third, which is your mean. But what if we were to say, here's how many you have, and here's your mean, what was the sum up here? You can calculate that. Just a quick example, if we tell you that 12 divided by 4 equals 3, but we take one away, well, with what you still have left, you can still calculate the missing one. So that's all the emphasis you really need to understand with summation. You won't be given the specific formula and say, hey, work this correctly. If you follow the examples done in the lecture as well as what we might do here in review, you'll know what you need to know in regards to summation and the formulas, but be able to work with those formulas. When you look at a question, you're going to have multiple choice answers, but you will need to do the work by hand, and you'll turn that work in. So you'll not be using SPSS or any other thing for that. However, you will be able to know, here's what the question is asking for, here's what it gives me, so here's what I have, what do I need? How do I work the formulas to get what I need from what I have? Which is really no different from anything else you've done in other math classes. Although the emphasis here is going to be on theory again, not so much the math. Alright, so I'll stop this video here, and the last one will be talking about variance and standard deviation.